Have you ever been curious on how to do a CFD analysis? Well, to find out more, watch this video. Hey guys, it's MJ Sanga, your creative engineer. So, in today's video, I'm going to explain to you what CFD is, what it's used for, and why it's important. For starters, CFD stands for Computational Fluid Dynamics. So most of you who thought it was CFD in business, no, it's not. This is CFD in engineering. To explain further, it is a science analysis method that uses digital computers to produce quantitative predictions of fluid flow phenomena based on the conservation laws, such as the conservation law of mass, momentum, and energy, governing fluid motion. In layman terms, it's an analysis method that helps you analyze the fluid flow of certain engineering systems. For example, rockets, planes, helicopters, pipings, and so on. We can analyze how these systems work under a certain fluid flow using the conservation of mass, momentum, and energy. CFD allows engineers to simulate fluid flow and heat transfer in complex systems. This provides invaluable insights into design optimization without the need for physical prototypes. So this is similar to finite element analysis, except in finite element analysis, we mostly check how our design is affected by external loads, momentum, and so on. Now, the importance of CFD can be understood in a few key points. At number one, cost-effective iterations. One of the primary advantages of CFD lies in its ability to facilitate cost-effective design iterations. Traditionally, engineers would need to build a physical prototype to test different design configurations, a process that can be time-consuming and expensive. However, with CFD, simulations can be conducted virtually, allowing for rapid and economical exploration of various design alternatives. In a scenario where building a prototype is cost-effective and could cost more than building the final product, CFD can help you check where your design is failing. For example, if you're designing an HVAC system or a pipeline system, CFD can help you analyze where the cracks and leakages can come out of your system. This can help you improve your HVAC piping system in a matter of minutes and seconds. Another one is performance prediction. CFD provides engineers with a predictive tool to anticipate how a system will behave under different conditions, whether it's accessing aerodynamic performance, fluid flow patterns, heat distribution. CFD simulations allow for a comprehensive understanding of a system's behavior before the physical prototype is even created. An example can come when trying to test out different materials. Like the first point, it would be very costly to build prototypes of different material structures. However, with CFD, we can be able to analyze our system by changing the material parameters from steel to maybe iron and doing a comparative study to see which material helps our system or our design perform better. Another importance is the optimization of energy efficiency. In today's world, where energy efficiency is a top priority, CFD plays a crucial role by simulating fluid flow and heat transfer. As engineers, we can optimize designs to enhance energy efficiency in a wide range of applications, from automotive systems to industrial processes, leading to reduced energy consumption and environmental impact. And lastly, insight into complex phenomena. There are certain fluid dynamics phenomena that can be extremely complex and challenging without the aid of CFD. Examples can include turbulent flows, shock waves, and intricate heat transfer patterns. CFD will allow us as engineers to view and analyze these complexities, enabling us to make informed, better decisions on our designs forward. So with these 4 points, you see why CFD is important, more especially in the 21st century where designs are very complex. As you see in the 21st century, as technology is constantly improving over time, we see that there are complex machines and products that are being made. CFD helps us analyze and see what we can do to improve our product or our design before it is actually manufactured. Seeing the problems that we have in our design can help us comprehend how our design can actually work in the real world. So then, it's rather better that I show you how CFD works by analyzing a part or a product. And for that, we're going to use an exhaust manifold. Now, an exhaust manifold is a part of an engine that collects exhaust fumes generated by the internal combustion engine. It conveys them towards a catalytic converter or turbocharger. Firstly, you need to note that the forces acting on the exhaust manifold during operation are immense. And let's not forget the high temperature that it absorbs from the gases. Now, with CFD, we're able to analyze which material is better for casting when producing our exhaust manifold. So I designed a simple exhaust manifold using SolidWorks. This is a generic design and I do not own any rights to this design, but this is just to show you how CFD can be used to analyze how this exhaust manifold will work, whether it will be efficient for the design or whether we need to improve it by either increasing the holes inside or changing the material. Now, as an engineer, it's good to design things and it's good to know how to design them through CAD software. But we need to ensure that the design that we've made is actually good for use in the real world. So let's imagine that this exhaust manifold is going to be cast produced in a certain factory. Now, the test that we're going to do on our CFD is based on a material impact analysis. By that I mean, we're going to do an analysis where our exhaust manifold will be under two different materials, for example, steel and iron. We then do a fluid flow and heat transfer on our exhaust manifold. We then do a comparative study to see which material would be better to create our exhaust manifold. So ideally, cast iron and cast steel are mostly used in modern day exhaust manifolds in your cars. But what if the company we're working for, ideally, in our imagination, wants to use a different material? So what we'll do is compare the material that we want to produce our exhaust manifold with cast steel. And in CFD, we'll have two materials. Cast iron, which is used in modern day production of exhaust manifolds, and our material B. So the first thing that was needed was to design a 3D model on SolidWorks. With ANSYS, it has a lot of analysis systems that will help you decide which system to pick for your analysis. This mostly depends if you're going to do a static structural, heat analysis, vibration analysis, and so on. There are a lot of analysis systems in this software. For reference, I'll be using articles and research papers that are already written in the CFD analysis related to an exhaust manifold. After we open Fluid Flow Sim, we then need to upload our exhaust manifold into the software. Please note that in order for your file to be read by ANSYS software, it needs to be saved as a step file. If you upload it as a SolidWorks part, it will not read it and will consider it as an error. So always save your part as a step file if you want to transfer it to another CAD or CAM software. So when we open Design Modeler, as you can see, we can see our part, but we need to generate it. So we click on generate, and as you can see, our part is there. From there, we need to make what is known as an enclosure. An enclosure is just the volume that passes through the internal of our exhaust manifold. This volume will be represented as the pathway or the fluid for what we're going to use in our analysis. To do that, we go on Insert and we click in Fill. So after we click in Fill, we need to select the internal surfaces of our exhaust manifold. I need you to note that depending on your design of your exhaust manifold or whatever you are going to do a CFD analysis on, there might be small surfaces that are not connected. That will require you to zoom in as you're selecting the surfaces. So this requires you to be precise and thorough. So then after we're done with our fill, we exit our design modeler and then we right click on our mesh. When we open our mesh, this is the interface that's given to us. So we first need to define our inlets and our outlets. So the outlet is the bottom of the exhaust manifold and the inlet are these four entrances right here. So afterwards, we also need to define the fluid. We always do this when we're creating our mesh. You can also do this in Design Modeler, but doing it in mesh is much better. So after we indicate all that, we then go to our meshing. So we select the inflation, and under inflation, we select the internal surface and the 4 outlets and the inlets of our design. Afterwards, we then click generate, and this is an already generated mesh, as you can see. For the setup, this is actually a long process, but I'll just summarize what I did in that process. So it is in the setup that you indicate what material is going to be used in the exhaust manifold as the analysis. You also have to indicate what fluid you're going to use. In most articles, it indicates water vapor or nitrous oxide. For this analysis, I used nitrous oxide. I also had to indicate what model I am going to use. So the model specifies what you are going to look for in this analysis. For this analysis, I turned on the energy, fluid flow, and the temperature. The type of fluid that I used was the SK omega. If you're dealing with a laminar flow, you can switch the type of fluid flow. If it's a turbulent flow, you can also switch the type of fluid flow. Just click edit and select the type of fluid flow analysis that you're going to use. I also had to indicate the speed at the inlet of the exhaust manifold, which I selected as 4 meters per second, and the temperature which will pass through, which I selected as 60 degrees Celsius. Afterwards, I did create a speed report and a temperature report. Afterwards, I then made sure that everything was okay. I clicked on initialize and I ran my calculation. So after all that is done, as you can see here, there are 2 fluid flows here. So our fluid flow A is for the steel material, while our fluid flow B is for our titanium material. Okay, so now that we're done with our simulation, we can now check the results and do a comparative study of our 2 materials. As you can see, when it comes to our pressure distribution, because of the shape of our exhaust manifold, the pressure is actually the same. The pressure is actually in its highest at the entry of the exhaust manifold. However, when we look at both analyses of the materials, we see that there's actually a lower pressure on the exit of our exhaust manifold. This just shows that the pressure reduces when our gas comes out of the exhaust manifold. However, the real difference is at the temperature. If we do a temperature contour on our titanium body and on our steel body, we see that the temperature distribution on our titanium manifold does not reach any high temperature levels. But if we look at our steel manifold, we see that there are high temperatures at the inlet of our manifold. Now, when we do a static enthalpy analysis, it is the same as our temperature. As you can see on our steel, it shows that there is a high enthalpy on the inlet of our exhaust manifold when we're using steel as a material. However, when we check our static enthalpy of our titanium manifold, we see that the enthalpy is actually mid-range and doesn't actually reach high levels. So, from our analysis, we can conclude a few things. At number 1, we know that titanium has a high temperature resistance. This has been proven through our analysis. The titanium retains its strength and its integrity at high temperatures, making it suitable for use in exhaust systems where temperatures can reach extremes during operation. The second thing is that titanium has lower thermal conductivity compared to steel, which can help reduce heat transfer from the exhaust gases to the surrounding components or environment. This can potentially improve the efficiency of nearby components and reduce the risk of heat-related damage. It is also essential to note that titanium also has some drawbacks to steel, including higher cost and more challenging fabrication processes. Additionally, titanium may not be suitable for all exhaust manifold applications, particularly those where cost considerations or specific performance requirements favor other materials. However, this is just a demonstration to show you how CFD works and how its applications can be used. not just for cars, but for aerospace, robotics, and so on. Also, like I said, as engineers, we're meant to solve a problem. And we did solve a problem by finding out a different material that can be used aside from steel. And that concludes our study. I will make a paper on this and maybe try and publish it. So look out on my LinkedIn to see when I'll be done and if it will actually be accepted. And there you have it, the mind-blowing engineering of CFD on a basic level and its applications. If you really enjoyed this video, please hit a subscribe and like and share it with your fellow engineers to let them know about CFD. Also, if you really enjoyed this video and you want to see more simulations, please leave some suggestions in the comments and let me know what simulations you would like to see done. I really hope you enjoyed this video. Please have a great day.